Okay, hi grade 12s. Welcome to our unit number 3, and we're going to study energy changes and rates of chemical reactions in this unit. So it's a unit where we get to look at our regular old chemical equations, but now study the heat. So if heat is gained or if heat is released, we're going to talk about that in terms of whether it's endothermic or is it exothermic. Okay, we're also going to look at some stoichiometry, so figuring that out, the ratios using our balanced chemical equation, and then we're going to finish off the unit with our rates of reaction. Okay, so hopefully you watched the demo video of the world's largest elephant's toothpaste experiment. That's a great little demo to do, and of course we don't do it on that kind of a scale that Mark Rober did in the lab, but we usually do that experiment. It's nice to see a few things. One, of course, it's exothermic. You can actually feel the heat coming off of that equation or that reaction. It's really quite warm. You can also review things like gas testing, because what's inside of those bubbles that form, it's oxygen gas. So you can do a gas test for that. You can relight your little splint and it will reignite. And it's just kind of a fun one to do. Okay, so anyway, let's get into energy changes and rates of reaction. This little video goes over pages 7 to 9. So it's the first part of the learning for today. Okay. So on page number 7, you're going to start there and you're going to have a look at some basic definitions. What do we call heat? So in chemistry, we call it enthalpy. Enthalpy, that's what we refer to as heat, okay? You'll notice that as you work through these little blanks on this page, the answers are on page number 9, so you can just certainly go ahead and check your own answers as you get there. But it just has to do with that law of conservation of mass or energy, right? So the energy going in has to be equal to the energy coming out. So you can think of it in terms of, is heat needed to be applied on the reactant side, or is heat escaping on the product side? Because the total amount of energy that's stored in the bonds and that is given on the reactant side will be equal to the total amount of energy on the product side, okay? Whether that energy is tallied up by the bonds that are formed of the new products and then the heat, vice versa, okay? But there's always a balance in the total number of amount of energy gained and released in a chemical equation. All right, and when we write out the chemical equation with the heat added into it, it's either expressed on the reactant side or it's expressed on the product side. We can just show that in a couple of different ways. Okay, so we're going to go over here. You're going to talk about that law of conservation of mass and energy. Okay, what are we talking about here? Review that idea of what we're saying when we say we're looking at an overall system. Okay, imagine it was closed in, what would be occurring and how you could measure that. And then the last thing in this little diagram, this paragraph, is to just note how is it that we specifically refer to enthalpy. So enthalpy is going to be H, okay? So our change in enthalpy, our delta H for any given chemical equation, how do you figure that out for the total chemical equation? You're going to take the amount of energy in the products, subtract that from the amount of energy on the reactants. It will give you a value. If the value is positive, then that means your thermochemical equation is endothermic. And if the difference between those two is negative, then your thermochemical equation is exothermic, because you're going to have a negative enthalpy. Okay, so that formula, again, you get it from the H, or the enthalpy of the products. So we're just taking the difference between the two, and that's your delta. Take the energy of the products, subtract that from the enthalpy of the reactants. Okay, and if you end up with a negative enthalpy, that is associated with an exothermic reaction, whereas a positive enthalpy, a change in temperature change between the two, then that is an endothermic reaction. So it's actually not too tricky. What kind of units are you using when you're measuring heat? Well, we're looking at joules, so capital J. Okay, so let's go through, I'll do a couple on here and then I'll let you go back and fill in the page. You can pause the video and fill this in and then check your solutions. So when we're talking about an equation, so we could be looking at just a change in state. We could also be looking at a chemical equation. So you've got both down here, a couple of different examples. So that's what you're putting in the first column. Is it a chemical equation or is it a physical change? Okay. So for the first one, here we have a combustion reaction. So you've got methane reacting with oxygen, giving you carbon dioxide and water. You certainly know where the heat is in that equation because it's exothermic, and that would just be a general knowledge kind of a thing in chemistry. Clearly, a combustion reaction produces heat. So you could write that chemical equation and you know that the heat's going to go on the product side because it's exothermic. So what would that show as the enthalpy? It would be a negative value because the heat is on the product side. Okay, if you were to add up all of the amounts of energy that are within those bonds for the total amount on the reactant side and the total amount on the product side, you could actually calculate that, and we certainly know how much energy is between a carbon-carbon bond, between a carbon-hydrogen bond, an oxygen-oxygen bond. So you could look up those values and tally them up. What would you find? You'd find that there's certainly more energy in total on the reactant side between the bonds of the reactants than there is in the products. So therefore the excess energy is on the product side. And in a chemical equation, that shows up as heat being released, and it is an exothermic reaction. Okay, so if you did the enthalpy calculation where the total amount of heat or energy of the products subtract the amount of energy on the reactant side, you're going to end up with a negative value. Okay, and that translates into an exothermic reaction. So as you go through here, you have to not only just be able to recognize some of that general chemistry, or you can simply look at it and it'll tell you where the energy is, and then you can recognize it as endothermic or exothermic. Okay, so put a little thought into this because I bet you can figure it out. The second one on that list, you see there, you've got salt. So we're looking at sodium chloride, and you can see that that is representative of a physical change because it's just dissolving salt. Now, back in your chemistry basic knowledge, do you remember, is a dissolving of a salt, is it endothermic or exothermic? So you're going to have to remember that, right, dissolving a salt is endothermic, unless it doesn't follow the rules, and there's only a couple we're going to memorize for that. So you know that that is a endothermic reaction, and if it's an endothermic reaction, then the heat would be on the reactant side, and it would have a positive delta H. Okay, go down to the next couple here. Let's look at these ones. Sometimes students get to grade 12 chemistry and then they get all confused with something very simple like just a change of state. Where does the heat go on these ones? And I always just say, well, you know, read the first one. If you've got a solid going to a liquid, what side do you add the heat on in order for that change of state to go on? And then you're like, oh yeah, I add the heat to the reactant side, okay? So now you're looking at that change of state, that's an endothermic reaction. Whereas if you read it going from a liquid to a solid, you're like, right, the heat is still on the solid side. So written that way, it's going to be exothermic. Okay, so there's some there that are just kind of general knowledge that you're going to actually just think about. And then I bet you will be able to know the answer to those. Okay. Once you've got that done, like I said, the answers are on page number 9. So you can check your answers with the solutions that are already posted there. All right, once you've done that page, you're going to scoot to page number 8, and we're going to learn a little bit about the specific heat capacity, calorimetry, and standard state conditions. So you're going to work through a couple of textbook questions, okay? There's some definitions here. Look up what specific heat capacity is. Basically, we're looking at what's a value that you would be able to know how much energy does it take to change a certain amount of a substance by a certain change in temperature, okay? I'll give you an example. Water, for example, has a very high specific heat capacity. It means that water takes a little bit of time to heat up and cool down. right? You can think of this in terms of if you live near a lake in the summertime. If you're lucky enough to visit a cottage, you probably recognize the fact that the water is pretty cold at the beginning of the summer, but as the summer goes on, clearly the water is hot, right? So it takes a little bit of energy. It has a high specific heat capacity, and that's a physical property that water has. Different substances will have different specific heat capacities, right? And that is something that you will then be able to transfer into doing a heat problem. And you're going to be transferring that information of specific heat capacity into this formula right here, where we're looking at the total amount of heat, and that's going to be equal to the mass times the specific heat capacity of a substance times the change in temperature, and that'll tell you how much heat has been absorbed or released in a chemical equation. Okay? So give that a go. We can measure that in the lab using something called a calorimeter, okay, where it's like a closed system where you can watch the water and record the temperature of the water. So for example, if you have a chemical reaction or a physical change, whatever it happens to be, you've got a chemical equation. And within that chemical equation, you know that there's a change in temperature. Okay, so let's say I want to put something like I want to put some sodium hydroxide into water and I want it to dissolve. Well, I can make an inference about how much heat is released in that dissolving process by how much heat is absorbed by the water where the dissolving is taking place. So I know how much energy it takes to create a temperature change for water. So if I know the mass of water and I know the specific heat capacity of water, which you will know because you will look it up in the table in the textbook, and I know the temperature change, then I know how much heat the water has absorbed. I can tell you then that's how much heat was released by the dissolving of the salt that was in it. Does that make sense? There's a little video I'm going to get you to watch that explains calorimetry a little bit more. Okay? All right, so you're going to work through these heat transfer problems, and some of them can be a little bit tricky, but I want you just to note that it can be hard to keep track of these negative signs, and you can almost do the entire math equation without factoring in your negatives and positives until the very end of the equation. So if you watch some of my solution sets, you can see that, right? And it just makes sense. Like, just did the temperature go up or did the temperature go down? And if the temperature went down, then it got colder. If the temperature went up, it got hotter. But sometimes when you add a negative in, it makes a little bit, it just makes it a little bit harder to problem solve. Okay, so they're a little bit tricky, but I want you to work away at those problems. Okay. When you get to the very bottom, this is where we are going to apply our knowledge of stoichiometry to a thermochemical equation, because you remember we're going to use stoichiometry in every unit in grade 12. You learned about this in grade 11. It's about the ratios. And so when we're looking at a thermochemical equation, this should make sense that if you have a little bit of product produces a little bit of heat, what if you have a whole lot of product or reactant? How much heat is that going to produce? Right? So you can scale it up or scale it down. So look at this one right here. You've got a thermochemical equation. And again, let's just stress here that when you write the energy right here in the equation, you would write it as such, plus 1,408 kilojoules. If you were to just write it as the enthalpy for that reaction, you notice that the heat is on the product side, so it has a negative enthalpy, and you would write it as such. Do you see that? The negative means it's exothermic, and when you write it in the equation as a thermochemical equation, the negative just means put that energy on the product side. Okay? If it was a positive enthalpy, it would mean that this is an endothermic reaction, and you would put that amount of energy written right into the equation, but you would just express it on the reactant side. Okay, so that's a bit of the setup. Now what do we do with that information? Well, you would read it as such. 2 moles of aluminum reacting with 3 moles of chlorine gives me 2 moles of aluminum chloride. In that ratio, 2 to 3 to 2, it produces 1,408 kilojoules of energy. What if the amount of the reactant was doubled? Well, here is where you take the energy and you double it. If it was halved, what would you do? You would half the amount of energy, okay? So given that example right there, I'm gonna get you to work on question 10 and question 11 and simply write out your equation and write out your thinking for these ones, because this is probably the hardest type of question we're gonna do from today's lesson. Okay, good luck with that and let me know how it goes.